Hello, everybody. In this video, I'll be going to go ahead and make sure to run through what is all about the right invariance equivalence relations in automaton. So, as what we have discussed last meeting, that we actually pertains to the relation. So, as we define relation, especially in our mathematics, that is also useful since that is the way of associating those elements with each other, for example. So say, for example, with that we do have here, let me just give you a set of example, especially for dealing with subset and set that is actually according to the mathematics theory then. So suppose that we are having the x is equals to a, B, and C. So how can we portray the relation pertains to that? Say, for example, this is in regards to Q0, Q1, then Q2. And they do have, I don't know, let's run through. This is A, this is B, Q2, and this is Q3, which will be like that. So this in mathematics, the relations right there, they are pertaining to A is to B, they do have relationship, and A is to C, and they do have relationship, something like that. All of the subset that we can form in this particular X, like for example, B to C, then C to A, and so on and so forth, which is valid relation still. So in our automaton, we can define that in since here then A is related to B and A is related to C, B is related to C, and C is related to A. So our goal for the equivalence relation, there will be a three rules in equivalence relations actually that we'll be going to focus with. There will be a reflexive in terms of automaton. Um Here, this is our initial state. Be mindful. So, in terms of relations, for example, A is related to B because they do have a relationship, and B do have relationship to Q2, whereas input B and Q2 is related to Q3. So, how can we define, especially since there will be a three properties in terms of automaton, which will be we are focusing to the reflexive property, and there will be symmetric, and there will be also the transitive. So let's try to run through pertains to that one by one of how can we define those properties in terms of which will begin to relate that in terms of automaton. So let's try to run through first the property of reflexive. For reflexive, that is actually every element of your X, for example, they are related to the S. So X is related to they itself, for example. So to be easy, X is related to itself. So this the relationship. So in your automaton, if we do have a value, or if we do have such what do you call this one? Okay. If we do have, um, I'm sorry, there is student who is chatting. Okay. Anyway, so in our automaton, when we say reflexive, this is how it works. Q0 is actually reflect with input A, that is A is to A. That is Q0, no. Transition A is still Q0. So therefore, once we'll begin to input A in our Q0, it will always loop. That is the theory of reflexive. So in our um set earlier. For example, for the A, B, and C, when we say reflexive, in terms of that one, we do have like A is to A, there will be a B is to B, and there will be C is to C. So they are reflexive to each other. So since every um element of X is always reflective. I mean, if is always related to itself. So that's how we define reflexive. So here then, Q0 is reflexive since that is looping to itself. We can also define as Q1, then as B, that is also reflexive. So that's how we define in automaton then. So hopefully that is somewhat clear to everybody. Now, for the symmetric, for defining symmetric, that is really so simple as well. Because in symmetric, if the x is related to y, then y is also related to x. So if your x is related to your y, so therefore, that is also related to vice versa. So how can we define that? In our mathematics, when your x is, we have an input of b and c, it must be that A is related to B and vice versa, B is related to A. And A is related to C and C is related to A. Could be B is related to C and C is related to B. That is symmetric. So in our automaton, how can we derive that? For example, that you do have a state of Q0, then Q1, and this will be your final state. For example, let's say that we do have two sets states only. And how can we define symmetric? So Q0 do have a relationship of A. So if they do have a relationship in terms of input A, there must be a Q1 relationship of A as well. So there it must be um so the I'm so sorry. In terms of the transition, in terms of Q0, where input A, it must go to Q1. And for Q1, input A, there must be Q0. So they are reflexive. Since they do have relationship in terms of A, they do have the same equivalence actually. So that's how we define that one. So we do have another. If Q1, Q2, if input B, there must be Q2. So Q0 input B will be equivalent to Q2. So therefore, Q2 input B, it must be equivalent to Q0. So that's actually how it works for the symmetrical. They are symmetric. They do have the meaning from the first state. It also implies with the second state. So vice versa na sila actually. So um, if Q0 is equivalent to do have a relationship to Q1, there must be Q1 direct to Q0. So that's simple. Hopefully that it is clear for everybody. That's um I know that you are that you know how to define with that one. Now, in terms of in terms of transitive as well, let's try to proceed with transitive. So for transitive property in terms of the equivalence relation, this is actually if x is related to y and y is related to z. So therefore, z must be related to x as well. So it must be that in your x in mathematics, if a, b, and c input c, so there must be that a is related to b and b must be related to c, and therefore it will goes back to a. The C must be related to A. That is transitive. They are forming like a cycle. So what about in automaton? How can we portray try that in our states, for example? So Q0 must have a relationship in terms of um Q0 to Q1. They do have a relationship in terms of A. And what about for Q2? There must be a relationship as well. So this is this is the relationship wherein we do have input B. And for that one, Q2 must return to Q0, which we can have, say for example, it could be A as well. So this is actually one of the example of transitive, wherein from your Q0 do have a relationship direct to Q1, and then your Q1 do have a relationship to Q2, and your Q2 must also have a relationship to Q0. So therefore, your transitions for that will be input A direct to Q1, and then for Q1, input B, we have Q2, and Q2 direct of A direct to Q0. So therefore, Q1, Q2, and Q0, that is actually transitive. So that is really so simple because in transitive property, there any states must be related to any for example, your initial state must be related to this following or the following states that you do have, and then afterwards the following states must also be related to any non-final state or final state, and the final state must also be related to your initial state. That's how it works here then in your automaton. So in this case, whenever we do have whenever every x will be related to y, and y will be also related to z, so there must be any x, or there must be any x related to z. That means to say that in our automaton, where in every final state must be related directly to your initial state. So it must just like forming like as a cycle. So that's how it worked in the right invariance equivalence. So those are the properties that we are actually dealing. So just make sure that an equivalence class is a subset of the set S, where all elements in that subset are equivalent to each other under specific equivalence relation. So that's how we were able to do it based on those properties that we've discussed earlier. So partitioning a set, that's what we have here in our presentation last meeting. That's not really important actually. Since as long as you really know their equivalence, so that's actually I know that it will gonna work. So in your examination, if such specific states, if I will be going to give you a specific what they call this one, automaton or a graph, you can just simply say, or you can just simply um do it like this, form a transition, and then you can just describe if what will be the properties that this particular graph or particular automaton following with, so that you can we no you can just simply discuss that one if ever that in your examination it will definitely re, what we call this one, kung ara gid bala. So let's try to let me check in your deliverables if there will be something important here. So, anyway, that is really ano naman. Okay. This is not really important. So, in the right invariance for all x. Okay, that's okay. Now, so if your x is related to y, then x must be all of the string. Okay. Now, this is actually for the automaton right invariance. We also do have here, if any x related to y, then any X, string of X must be also related to Y string. So that means to say that your Q0, what will be the string of your, if this will be your X, that accept, for example, it must be also equivalent to any each other, any particular set. So say for example, Q0 direct to Q1, it will print out A. So if you will begin to form a structure, state Q0, no, Q0, Q1, and then input A and B. So from Q0, if we will input A, it must return to Q1. And for from Q1, if we will input A, it must return to Q1. So therefore, it will become like this. If input P, if we form a structure for this one, um, QB, for example, Q0, it must return to no, it must return to Q0. And from Q1, must return to Q0. So they are actually balanced, or they do have a right invariance equivalence, wherein since in our discussion that in any X, that if X is related to Y under the equivalence relation R, then appending the string for to both X and Y will preserve the relation. So therefore, the relation does not change when extended by the strings on the right. So as what we can check here, that any state according to the graph that we do have here, that any Q1 string and Q2 string, where will be the where it will be, what will be the transition, or what will be the input for that one, it must ensure that the behavior of our automaton is consistent across any input string. So that maintains the equivalence of the states after processing our string. So that's how it works in our states of automaton here. So say for example, let's try to see. I want you to assess, for example, if this one, if this follows with the right invariance, you can just simply say Q0 input A, um, input A, and input A. And this will be input B, and this must be input B, input B, input B. Let's try to see if this follows with those right invariants that we do have earlier. Since in our in that string that we were able to know, since in right invariance it will maintain the states or the transitions or the results or whatsoever where it will proceed. So that's how we will begin to check here then. So we will just work on it one by one. So we do have steps accordingly. Let me check if I have. Okay, the steps that I have given into your presentation is different. Okay. All right. We'll just have to check this one if this follows with the right invariance, or what states do have the right invariance as well, so that we can define also. So from states that we do have, we have Q0, Q1, Q2, and Q3. So from input A and input B, Q0 input A will be going to Q1, and Q1 input A will go to Q1, Q2 to input A will go to Q1, Q3 to input A, Q1. So therefore, that is following the right invariance. Now, let's try to run through here then for the B, if this follows with the right invariance as well. So we can send right invariance rather. So for the input B, always do know that any string of X must be related to any Y string as well. So if this will be your X and this will be your Y, in every state that you do have, um, it must return with the same um no. If this is your X and this is your Y, it must have the same results. So that's how it works. So this is the state, and this is the string, and this is the string. So this is the string that we do have, the string A and B. Now, so from Q0, the rec of B that is going to Q0, and Q1 to um Q1 input B, Q1. Q2 input B, Q2. And Q3 input B, it is actually going to Q3. So therefore, in this one, this is not following the right invariance. However, in that one, what we do have in this particular state, in this particular set of automaton that we do have, it's not following the right invariance relation. However, it portrays also it has the equivalence relation if we are dealing with the equivalence relation. But we are just focusing into the right invariance relation. So in right invariance relation, make sure that for all of the particular state, uniform ang ila nga transition. So therefore, here then, if from Q0, the input B for Q0, it must contain Q0. So if and only if, let's try to change the path para mag-equivalence sa, for example, because, okay, let me, okay. So for Q1, it must go to Q0. And Q2, Q0, and Q3. So B. So therefore, right now, we can assess that this is definitely following the right invariance relation rule. So in your equivalence relation earlier, we do have Q0 do have the equivalence relation portraying the transitive. I don't know, that's actually reflexive. This is reflexive. And Q1 earlier, returning to Q1 is reflexive as well. And Q2, that is reflexive for the equivalence relation. But of course, it does not follow or it does not accept the right equivalence relation. Because in right equivalence relation, any input, any state must have the same or equal input of string and must also be maintaining these states as well. They do have relationship. So if X do have a string, this is the state Q0 and this state Q1, they must have a relationship of strings that accept as well, that holds. So kung bakadto siya sa Q1, dapat Q1 man. So that's how it works. So this is the hopefully that it is clear, but I just wanted you to just explain in terms of those implementations, if ever in your examination it will be there. So thank you so much. Hopefully that it is clear for the right invariance equivalence relation, and for the for the right equivalence relations. Those are the implementations that we'll begin to run through. So hopefully everything's all clear right now. And in our next video, we will deal with the pumping lemma already. Okay. So see you there.